In this lecture, we are going to study about losses in optical fibers. This is lecture 10 of unit 4, chapter fiber optics. Seen that when light signal propagates through a fiber, it suffers loss of amplitude and change in shape. The loss of amplitude is called as attenuation and the change in shape as distortion. Attenuation, the loss of optical power as the light travels down a fiber, is known as attenuation, or it is a ratio of input optical power into the fiber to the power of light coming out at the output end. The attenuation coefficient is given as alpha is equal to 10 by L log to the base 10 pi by p naught decibels per kilometer, where pi is the input optical power and p naught is the output. Attenuation is mainly due to absorption, scattering and bending. We shall see each of them. Absorption losses. In glass fibers, three different absorptions takes place: ultraviolet absorption, infrared absorption, and ion resonance or OH minus absorption. What is UV absorption? Absorption of UV radiation around 0.14 micrometer results in the ionization of valence electrons. That is, the electrons will jump from the valence band to the conduction band. Infrared absorption, absorption of IR photons by atoms within the glass molecule, causes heating. This produces absorption peaks at 8 micrometer, also minor peaks at 3.2, 3.8 and 4.4 micrometer. Ion resonance or OH minus absorption. The OH minus ions of water trapped during manufacturing causes absorptions at 0.95, 1.25 and 1.39 micrometer. So these are the different types of absorption losses. Scattering losses. The molten glass, when it is converted into thin fiber, under proper tension, creates submacroscopic variation in the density of glass. Dopants used to change the refractive index cause inhomogeneities to be present and act as scattering centers in the fiber. This leads to losses. This is also known as Rayleigh scattering and depends on the wavelength of light. Scattering losses are inversely proportional to the fourth power of lambda. Wavelength below 800 nanometer have high Rayleigh scattering losses, and wavelength above 1700 nanometer have high losses due to IR absorptions. This is a graph between wavelength and attenuations. The various types, the Rayleigh scattering, OH minus ions, IR absorptions and UV absorptions can be observed on this particular graph. Now we shall see what is bending losses. Wavefront travels perpendicular to the direction of propagation. For this, the part of the mode outside the bend has to travel faster than that on the inside. But according to Einstein's theory of relativity, in a single wavefront, one part should not travel with a higher velocity than the other part. So the part of wavefront traveling in the cladding medium lost in the form of radiation leads to bending losses. The bending losses may be a micro bending loss or a macro bending loss. Micro bend is a small scale distortion. It indicates pressure on the fiber. This is where there is a pressure on the fiber. Macro bending is a large scale bend. You can see it is almost a 90-degree bend can be seen over here. When a fiber is bent through a large angle, it undergoes a strain. The bending strain will affect the refractive index and critical angle of the fiber in that area and leads to losses. We next see what is distortion. The light pulse transmitted through a fiber or of a given width, amplitude and interval. These light pulses broaden and spread into a wider time interval because of the different times taken by different rays propagating through the fiber. This phenomenon is known as distortion or pulse dispersion. It is expressed in units of nanoseconds per kilometer. So we have seen the different types of losses in optical fibers. We'll see a numerical. So calculate the numerical aperture, angle of acceptance and fractional index change for an optical fiber if the refractive indices of the core and cladding are 1.563 and 1.498 respectively. Now the formula is for numerical aperture is equal to sine alpha I maximum, that is equal to root of n1 square minus n2 square by n naught. What is given in this particular numerical? N1, the refractive index of the core, is equal to 1.563. N2, the refractive index of the cladding, is 1.498, and we know N naught is the refractive index of air, which is equal to 1. Substituting the values, we get numerical aperture is equal to 0.4461. What about acceptance angle? Alpha I maximum is equal to sine inverse of numerical aperture. So when you substitute that, you get the acceptance angle is equal to 26 degrees 30 minutes. Fractional index change del is equal to n1 minus n2 by n1. When you substitute the values, you get it as 0.0416. So this is one of the numericals which can be done for optical fibers. You can also calculate the critical angle. We know sine theta c is equal to n2 by n1. You can write out and calculate also what is the critical angle. So in this particular lecture, we have seen what are the losses and also one numerical related to optical fibers.